Hello, welcome back. This is probably the last lecture on the basic principal agent model. So in this lecture, I'm going to explain this generalized model. So before we get started, let me just go over what we have done. So in example 1 and 1.5, uh, so we basically apply these basic concepts that we discussed at the beginning of this semester, like backward induction, constraint optimization. So the purpose of considering example 1 and example 1.5 was just to understand the narrative of this basic principal engine model and just to apply these concepts from game theory and math. So it was just to warm up, okay? And then the second example, the example number 2 was an example which shows the tension between the insurance and incentive, which is the main topic that we want to discuss. So example 2 is basically the main example. So in example 2, we considered risk-averse agent and risk-neutral principle. So by assuming risk-averse agent, we could see the tension between insurance and incentive. We could see the inefficiency of inefficiency, which is caused by this the asymmetric information problem, the imperfection of the contract. So the but example 2 was, in a sense, it was too simple because the risk sharing problem was too simple. So we assumed the principle is risk neutral. So the first best allocation of risk is is that the principal takes all the risk and the agent gets no risk at all. So in other words, the agent is given a fixed wage and the principal takes all the risk. That's the first best risk sharing rule. So what we wanted to see was more complicated situation, like the situation in reality, like the principal is also risk averse and the agent is risk averse. So we want to think about the risk sharing problem as well. Not only the incentive problem but also the risk sharing problem. So the reason why we consider this generalized model is that so we want to see the risk sharing problem in detail in a more generalized setup. So and also we want to see that how far we can go. We derive the conclusion like there must be some trade-off between risk sharing and incentive because of this asymmetric information problem. But we wanted to see how much we can go, how far we can go, how much we can generalize this conclusion. Okay, so that's the reason why we consider this generalized model. Okay, so let's get started. So we assume the reservation payoff is U underbar, and the agent's effort is the effort space is the set of positive real number, and output space is continuous. So x can be very small, like x underbar, and it can be large, like x upper bar, and any number between those two can be a revenue. And let f of xa be the probability density function. So it shows the probability density when a, the effort level a, is given, and p's payoff is free. So at the beginning we assume that free is an increasing and concave function, and we will just stick to that assumption and we'll add no more. Okay, and the agent's payoff is u, and as the principal's payoff, we just keep the agent's payoff as assumed at the beginning. So we will add no more assumption on this. So small u function is increasing and concave, and c function is increasing and strictly convex. So that's it. Okay, so we don't add uh, any more assumptions on this. So this is quite general. So lots of functions can satisfy these assumptions, right? So for example, there are many increasing concave functions like square root function or log function. They are all increasing and concave functions, and you know we don't want to specify the v and u. So we will just you know take this v and u as they are, and we wanted to see we still can derive the conclusion that we did with example 2. Okay, so I said we'll focus on risk sharing problem in this generalized model discussion. So let's think about this problem. So this is the first best contract. In other words, it's full information benchmark, which means we can think of a wage function which is a function of effort. Okay, so this is the principal's problem. So the principal is maximizing the expected utility. So the principal's utility is now represented by this v function, and because the revenue, the output x is random, so we consider expected utility of the principal. So this integral is the expected utility of the principal. Okay, and subject to, there is one constraint which is the IR constraint, right? So the left hand side of the inequality is the expected utility of the agent, and the right hand side is the reservation payoff of the agent. So if the left hand side is greater than the right hand side, that means the agent is better off by accepting the offer. So by making sure that this inequality holds, the principal can make sure that the agent accept the offer, right? So so this is the principal's problem. You may want to ask, where is the IC constraint? The IC constraint is there, but we don't take it seriously because the IC constraint is not binding. Okay, so we only consider the binding constraints because binding constraints are important constraints that affects the solution of this maximization problem. On the other hand, non-binding constraints are not important constraints, so non-binding constraints can be ignored. So in this example, the IC constraint is a non-binding constraint, so we can ignore it. I will explain that in a minute. So let's just see this Lagrangian first. So because we cannot replace any of this W or something like that, so we have to use Lagrangian, right? But to write this Lagrangian, we have to be sure that the inequality constraint, the IR constraint, must be binding. But we know that the IR constraint is binding. So the IR constraint is binding, so we can write the Lagrangian as written in the slide, right? So the Lagrangian can be written like this. So the first we write the objective function of the maximization problem, and then we add lambda. What is lambda here? Lambda is the Lagrangian multiplier, which shows the importance of this constraint. So the interpretation of Lagrangian multiplier is something like the shadow price or shadow value of the constraint, right? So by relaxing constraint a little bit, how much you can improve the profit of the principal. So that's what this Lagrangian multiplier shows. So that's the meaning of this Lagrangian multiplier. So sometimes we call it shadow price or shadow value. Okay. So in the Lagrangian multiplier, we write the IR constraint, the binding IR constraint, and then we are going to solve this problem. But what's the choice variable? As before, the choice variable is the wage function. So we have to choose a function to maximize a function. So which is not really easy task, but conceptually it's not too difficult to understand. So, we're going to solve that problem. But before we solve that problem, let me explain why we don't have IC constraint first. Okay, the IC constraint is still there. Why we still have to think about the incentive of the agent. Okay, so IC constraint is still there, but it's not important. In other words, it's not binding. What that means is we can meet the IC constraint so easily. We can satisfy the IC constraint so easily, so we don't have to think about that. Okay, so in the full information benchmark, the principal can write a contract which is contingent on the agent's effort. Let's say W of X and A. So we have two arguments here, W of X and A. So the revenue X and the effort A. So these two are the contingent variables which the wage depends on. Okay, so the principal can give a very strong incentive by setting the risk sharing problem. The principal can give a very strong incentive setting the risk sharing problem aside with the following wage function. So let us define this wage function like this. So W of XA is W of X if A equals A star. So what that means is if the agent puts exactly A star much effort, then the principal will give W of X, which is still a function of X. So which still depends on the realized value of X. And the principal will give negative infinity if the agent doesn't follow the order. So the principal, so now we can write a contract which is contingent on the effort, which means the principal can be like a dictator. So the principal says, okay, you should do this, otherwise you should do this, and you should do it hard, very hard, otherwise I will make you suffer. Okay, this is what the contract means. So the principal specifies the effort level, or the contract specifies the effort level, which is set at the optimal level probably. And if the agent follows the order, so if the agent puts exactly A star much effort, then the agent will be compensated as much as W of X. But if the agent doesn't follow the order, then the agent will be punished. It doesn't have to be negative infinity, but just to be dramatic, just to be just to emphasize that just to emphasize, I just put negative infinity. Any small number, any very small number will work. Okay, it doesn't have to be negative infinity, which means there are infinitely many functions which can be used for this purpose. But for our discussion, let's just stick to this specific function. So if you follow the order, if you put A star much effort, then you will be compensated as much as W of X, otherwise you will suffer. Okay, that's the meaning of this. What this means is that when you decide how to share the risk, you don't have to think about the incentive, because incentive problem is already taken care of by this function. The incentive problem is determined, is solved by this function. So the principal gave an order, so the agent must work as much as a star, and you know and then we don't have to think about the incentive problem anymore. So that's the reason why we don't have to think about the IC constraint more, right? So the incentive problem is solved very easily. So the incentive problem is still there, but is trivial. So the incentive problem is already taken care of. So we don't have to think about that anymore. So that's why we don't need to consider IC again. Okay, so that's the reason why we didn't see the IC constraint in the principal's problem. Okay. All right. So then, okay, we want to solve that problem. Like we want to maximize the principal's expected profit, expected utility by choosing a function, choosing the right function. So choosing the right wage function. There are infinitely many crazy wage functions, but we want to choose one among them to maximize the principal's expected utility, which is not easy, right? So if you think about the possibilities of the wage functions, then it must be enormous, right? It's astronomous, right? So there are infinitely many possibilities, but we want to choose one among them. So how do you do that? How do you solve this maximization problem? Okay, so but it sounds difficult, but we already have done it in example 1, right? So in example 1, we took this W5 and W10 as scalar variables, and we regard them as like regard it as like there are two choice variables, W5 and W10, and then we differentiated the objective function with respect to these two variables like W5 and W10, right? That's what we did in example 1. Sorry, we didn't differentiate it, but you know what I mean. So we regarded these W5 and W10 as scalar variables, and we chose these variables. So that's the idea, right? So we wanted to do this. We want to do the same here. So we choose x0. So look at this diagram. So we choose x0, any x0. So some x0, and fix x0. We just focus on this x0, and we want to find w of x0, the optimal w of x0. Okay. So forget about all the other x's. We just focus on this x0, and we want to find the optimal w of x0. How do you do that? We differentiate the Lagrangian with respect to w of x0. And then what's the next step? We choose x1, and we differentiate the Lagrangian with respect to w of x1. Okay, so don't get confused. We don't differentiate the Lagrangian with respect to x0 or x1. We differentiate the Lagrangian with respect to w of x0 and w of x1, right? So x0 and x1 are just some numbers, so they are just possible revenues. So they are not our choice variables. The choice variables are w's. So we want to differentiate the Lagrangian with respect to w's. And then we repeat this process to find the optimal level of wage for each x. So we do that many times, and then we connect the dots. Then we'll see the optimal wage function like you see in the diagram, like w. We will find the w star function. by connecting dots. Okay, that's the idea. So we differentiate the Lagrangian with respect to w of some x. Okay, that's the idea. Yeah, so we did it, and then we rearrange the terms, and then we have this expression. So if the action is verifiable, thus constructible, which means if we consider the full information benchmark case, then the following equation characterizes the optimal contract for all x. V prime over u prime must be lambda. Okay, so what does this mean? V prime is the marginal utility of the principal. U prime is the marginal utility of the agent. So the ratio of these two marginal utilities must be lambda. What is lambda? We don't know. But what we know is the right hand side, lambda, is not a function of x. Okay, so on the left hand side, we have x's, right? On the left hand side of the equation, we have x's. But on the right hand side, we don't have x. So, if you take this x as a variable, then what that means is the right hand side is a constant. So, okay, the first interpretation, first observation of on this equation is that the ratio of the marginal utilities must be constant. So the marginal utilities must be the ratio of marginal utilities must be remains the same regardless of the realized value of x. So let's look at the second equation at the bottom. So what the first equation means is that just choose any x0 and x1, then the ratio of the marginal utility of principal and the marginal utility of the agent when the realized x is x0 must be same with the ratio when the realized x is x1. So regardless of the realized value of x, the ratio of the marginal utilities must be the same. Okay, so that sounds okay, right? So this is the way to maximize the expected utility of the principal. And I also want to emphasize that I also want you to understand that this is also the way to maximize the social surplus, social welfare. Why is that? Because the IR constraint is binding, the agent gets a fixed expected utility. Okay, so the agent gets fixed amount of expected utility. So the principal gets the rest, right? So you bake a pie and you share the pie with your friend, and regardless of the size of pie, you give the same amount of pie to your friend. What that means is that if you make a bigger pie, then you will eat a bigger pie, right? So to maximize the social surplus is the way to maximize the expected profit, expected utility of the principal, because the agent will get the same amount always, right? So the agent will get exactly as much as you underbar, as much as reservation utility. So that's the what IR the binding IR constraint means. So the principal wants to maximize the social surplus, and the principal will give the surplus to the agent as much as just you underbar, and then the principal will take the rest. So the maximizing so in this model, in this very simplified model, maybe in reality this is not the case, but in this simple model, maximizing the social surplus is same with maximizing the expected utility, and vice versa. Okay, so this is the way to maximize the social surplus. So this equation characterize uh, the condition to maximize the social surplus. So and it makes sense, right? It can be understood. So the if you want to maximize the social surplus, then you don't want to change the marginal utility of the participants, right? So if the one if one player's marginal utility is very high while the other player's marginal utility is low, then you can give more to the player with higher marginal utility. That's how you increase the overall utility, right? So in at the optimum, the marginal utility of these two people must be they don't have to be same, but they have to be in some fixed ratio. That's what these equations mean. Okay, and also this is the way to optimally share the risk. So this is the way to maximize the social surplus. This is the way to maximize the principal's expected utility, and also this is the way to uh, the optimally share the risk. Okay, so this equation is the optimal. I call this equation later the optimal risk sharing rule. And the reason is, okay, so we have two goals. We we want to set the effort level optimal, and we want to set the risk sharing rule optimal. Okay, so the effort and risk sharing, these are the elements of utilities and the surpluses. So we want to maximize the social surplus. We want to make sure that the risk is shared optimally, and also we want to make sure that the effort the effort level is optimal. But as we said before, as you saw before, so the effort level is set optimal. Okay, so effort level is set optimal, and then what's left is the we want to set the risk sharing rule optimal. We want to risk to be shared optimally. Okay, so you see this equivalence, right? So the maximizing the social surplus is same here in this example, in this situation. The maximizing social surplus is equivalent to sharing the risk optimally. So you can see all these equivalences, right? So this is the way to maximize the social surplus, and this is the way to maximize the expected utility of the profit, and this is the way to share the risk optimally. Okay, and okay, so this is the optimal risk sharing rule, and let's try to understand this equation in more detail by considering these examples. So let's consider the first case. So what if this phi prime equals 1 for all x and u prime is not? So what that means is the phi prime, so phi prime doesn't have to be 1, but phi prime is constant. So that's the assumption. So what if the phi prime is constant for all x's? So what that means is the principal is risk neutral. So the principal's marginal utility is constant, means that the principal is risk neutral and the agent is not. So the principal is risk neutral, then what is the optimal way to share the risk? For the equation to hold, for all realized value of x, the wage should not depend on the output. Okay, so look at the equation. The numerator is 1, and we have denominator, which is function of x, right? And on the right hand side, we have lambda, which is not a function of x. So numerator is not a function of x, and the right hand side we have lambda, which is not a function of x, and at the denominator we have u prime, which may be a function of x, but then this equation cannot hold for all x's. So then what do we have to do? We have to set w of x to be constant. In other words, we put a fixed wage, we give a fixed wage to the agent. Then w of x will be just w. It will not be a function of x. Okay? If w of x is a fixed wage, then w of x will be just w. It will not depend on x. So then the numerator will be 1 and denominator will be some number. It will not be a function of x, and the right hand side we have lambda, which is not a function of x. So then this equation can hold for all realized value of x. Okay, so that's the only way. So what that means, so let me summarize the discussion. So what that means is the principle is risk neutral, then the agent must be given a fixed wage. So if the principle is risk neutral, then all the risk must be given to the principal. That's the optimal way to share the risk. Okay? So you can see that in this equation, right? And let's consider the next case. So what if u prime is constant? Let's say 1. So u prime is 1 for all realized value of x. In this case, all variation of x must be reflected to the wage in order to make this x minus w of x constant. So we saw this case in example 1. So and we called it selling the firm contract, right? So all the variation of x, all the variation of revenue is reflected to the age. So it's like the principal is selling the firm, selling the business to the agent, and x minus w is constant. Okay, so the principal is taking some fixed amount of money, and the business is now run by the agent. So the agent will take all the risk, all the responsibilities, all the benefits. So that's the idea of selling the firm contract, and that will be the case if the agent is risk neutral. So if u prime is 1, which means the agent is risk neutral, then the optimal way to share the risk is that the agent takes all the risk and the principal takes no risk. Okay, so at first this equation v prime over u prime equals lambda, this equation looks a bit difficult to understand, but as you see, what that means is it simply says that if someone is more risk averse than others, then this someone will be given should be given smaller amount of risk. Okay, the more risk player should be exposed to smaller amount of risk. So that's basically the idea. And we consider these extreme cases, like the principal is risk averse and agent is risk averse, risk neutral, and we could see our intuition works. Okay, so if the principal is risk neutral, then all the risk must be taken by the agent, and if the agent is risk neutral, then all the risk must be taken by the agent. Okay. So this is the optimal way to share the risk. Okay, and this is the first best contract. What about the effort? I said the effort is set at the optimal level, but I didn't show what that level is, but I will not show it. It's kind of straightforward to derive. So you can derive it if you want, but there is nothing really interesting there. So I will not discuss the effort level in detail here, but let's just focus on this equation and some variation of it later. Okay, so move on to the second best contract. So this is the optimal contract subject to hidden action problem. So again, we see this principal's problem. The principal's objective function is the expected utility. So principal's utility is v function, so expected utility is integral of v times f. So this is the expected utility of the principal, and we have two constraints here. The first one is the IR constraint, which must be binding. So this inequality constraint will hold as equality. So this will be a binding constraint, and the second constraint is the IC constraint. So it says that A must be an element of a set. So on the left hand side, so argmax blah blah is a set. So what that means is there may be multiple effort level which maximizes the agent's utility. Okay, so there may be multiple solutions. So that's why we say that this is a set. Okay, because there may be some multiple maximizers. And what is argmax? Argmax is the argument, which is A, that maximizes the following function, the expected utility of the agent. So so in plain words, what that means is the A must be a maximizer of the expected utility of the agent. Okay, but I want you to look at this A prime. So the argument of the maximizer, argument of this maximization problem is A prime. Okay, so A prime appears at the bottom of max, and on the objective function we see A prime. So this A prime is the choice variable, and the solution will be denoted by A. Okay, so A prime is employed to denote the argument of this maximization problem, the agent's utility maximization problem. So that A prime is the choice variable of the agent, and the solution of this problem, solution of this maximization problem, is denoted by A. Okay, you see the difference between A and A prime at the bottom. Okay, so this is the IC constraint. So the second constraint is IC constraint, first constraint is IR constraint, and now this W is just function of X. It's not a function of A. So the principal has to choose a function which is contingent on X, only X, to give an incentive for the agent to work, and at the same time the principal has to set W optimally to share the risk. Okay, so this W function has to achieve two goals. One is to optimally share the risk. The second goal is to give enough incentive to work. Okay, so as we saw in example 2, we can achieve two goals optimally, fully. Okay, because there is this trade-off between insurance and incentive. There is trade-off between risk sharing and incentive. So the first order condition of the agent's utility maximization problem can be written like this. So to rewrite the IC constraint like this, we have to assume that the first order condition approach works. So sometimes we cannot use this first order condition approach, but in our discussion, we'll assume that the first order condition approach works. So the agent's utility maximization problem can be solved. So the solution of it can be characterized by this equation, the equation that we saw on the top, and this is basically the IC constraint for the principles maximization problem. So the Lagrangian can be written like this. The first term is the expected utility of the principle. So integral v of x minus w of x f of x a dx. So this is the expected utility of the principle. And then we have lambda, which is the Lagrangian multiplier for the IR constraint. And then we have IR constraint, binding IR constraint. And then we have mu, which is the Lagrangian multiplier for the IC constraint. And then we have IC constraint. So this lambda and mu shows how important each constraint is. Okay. So this is Lagrangian. So as before, we differentiate this Lagrangian with respect to w of x. Right. So we fix any x, let's say x0, and then we differentiate this Lagrangian with respect to w of x0. So that's the way we maximize this function. Okay. And then by maximizing this w of x0, we derived the following equation. So if action A is not verifiable, so in other words, if we consider the hidden action situation, hidden action case, then the following equation characterizes the optimal contract. So the left hand side, we still have this v prime and u prime, the ratio of v prime and u prime. So it's the same as before. But on the right hand side, we have something more. So we have lambda as before, plus mu times f of a of x and a over f of x and a. So what is this f of a? F of a is the first derivative of f with respect to a. So f of a is the first derivative of f with respect to a. Okay, so by just looking at this, we have one we can derive one conclusion. So this second best situation, risk sharing, is not optimal, right? So how do you, why is that? So mu is larger than 0 implies that risk sharing is inefficient. Why? Because we have already seen the optimal risk sharing rule is given by this v prime over u prime equals lambda. So this will be the same as the optimal sharing rule we derived in the full information benchmark case, only if mu is 0. Okay, only if mu is 0, then this equation will be same with the equation that we derived in the full information benchmark. So why do we have this? Why do we have this mu? We have this mu because, you know, let's look at the bottom bullet point. The optimal wage is not fixed wage even if v prime equals 1. So what that means, even in the case that the principal is risk neutral, fixed wage is not optimal. The reason is the principal has to give an incentive to work. To give an incentive to work, you shouldn't give a fixed wage. So if a fixed wage is given, then the agent has no reason to work. So the agent will the effort will be 0. So to give an incentive to work, even in the case that the principal is risk neutral, the optimal wage must be a function of x, though the optimal wage must be contingent on x. What that means is risk sharing is not optimal. Okay, so we have this conclusion. We just derived the same conclusion that we derived in example 2, right? So still we see the trade-off between insurance and incentive. We see that the risk sharing is not optimal because of this asymmetric information problem, because the binding IC constraint. Because IC constraint is binding, in other words, because the principal has to give an incentive to work to the agent, the principal has to distort the risk sharing rule. Okay, so that's what we find. That's what we can see here. So in the second best contract, you can see the fundamental trade-off between the incentive and insurance. The optimal risk sharing is taking place if more risk is taken by less risk-averse person. At an extreme, the principal is risk neutral, in which case the principal must take the entire risk and the agent must be given a fixed wage. But then the agent has no incentive to work, so to give an incentive to work, the principal has to give a changing wage, non-fixed wage. Then what that means is, at the same time, what that means is the agent is overexposed to risk. Okay. So this is the idea. This is the first topic that is discussed in the Nobel Prize document, right? So the first topic discussed in the Nobel Prize document is the tension between insurance and incentive, and we have discussed that in very detail with this by analyzing this principal agent model. All right. So that's it for today. So and this is the last lecture on the basic principal agent model, but we'll see the similar thing later on. And I said this is the last lecture, but as a matter of fact, we'll have to discuss it a little bit more with the homework 2, right? So I'll explain this a little bit more with homework 2. Okay? Alright, that's it for today. Bye.